Tonight, we're diving into one of the strangest rules ever discovered about the universe. Nothing can go faster than light. Not a spaceship, not a particle, not even information itself. And here's the part that really messes with your head. This isn't just a cosmic speed limit. Without it, reality stops being self-consistent. The universe begins to contradict itself. And eventually, nothing works at all. And by the end of tonight, you'll see how a deceptively simple thought experiment by Richard Feynman revealed something so deep about reality that it still shapes everything we know about physics today. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The speed of light is exactly 299,792,458 meters per second. We usually round this to 300 million meters per second for convenience, but that exact number isn't arbitrary. It's measured, verified, and now it's actually defined as exact because we use it to define what a meter is. But here's what most people don't understand. The speed of light isn't just about light. It's about the structure of space-time itself. It's the maximum speed at which cause and effect can propagate through the universe. It's the speed at which massless particles must travel. It's the conversion factor between space and time in Einstein's equations. Light happens to travel at this speed because photons have no mass, but the speed itself is more fundamental than light. If light didn't exist, this speed would still be built into the universe. Call it the speed of causality, the speed of information, the speed limit of the universe. Light just happens to go that fast because it has no choice. So, why is there a speed limit at all? Why can't things just keep accelerating forever? Why does the universe have this bizarre constraint where you can never quite reach this ultimate speed, no matter how much energy you pump into an object? The answer takes us deep into the nature of space, time, mass, and energy. And it starts with a simple question that Richard Feynman asked. Richard Feynman was one of the greatest physicists of the 20th century. He won the Nobel Prize in 1965 for his work on quantum electrodynamics, the theory of how light and matter interact. He was known for his ability to explain complex physics in simple terms, for his playful personality, and for his deep physical intuition. He could often see the answer to a problem just by thinking about what must be true rather than grinding through complex mathematics. In the 1960s, Feynman was giving lectures on physics at Caltech. These lectures were recorded and eventually published as the Feynman Lectures on Physics, which became one of the most famous physics textbooks ever written. In one of these lectures, Feynman addressed a question that students often ask: why can't anything go faster than light? Most physics professors would start with Einstein's equations, derive the Lorentz transformations, show how mass increases with velocity, and eventually conclude that infinite energy would be required to accelerate something to light speed. That's mathematically correct, but it doesn't really explain why. It just describes what the equations say happens. Feynman took a different approach. He asked what would happen if something could go faster than light, not whether it can, but what would happen if it did. And he showed that faster-than-light travel leads to a logical contradiction so severe that it would destroy the very concept of cause and effect. The universe would become nonsensical. This is the key insight. The speed of light isn't just a rule that nature follows for no reason. It's required by logic itself if we want cause and effect to make sense. Let me explain Feynman's argument, step by step. Imagine you have two events happening in space. Event A happens at one location, at one time. Event B happens at a different location, at a different time. Now, there are three possible relationships between these events. First, event A could cause event B. Maybe event A is you turning on a flashlight, and event B is the light hitting a wall 3 meters away. The light travels from the flashlight to the wall, so there's a clear causal connection. A causes B. Second, event B could cause event A. This seems weird, but in principle, if we rearrange things, maybe information travels from what we're calling event B back to what we're calling event A. Causality runs the other direction. Third, the events could be causally disconnected. They could be so far apart in space and so close together in time that no signal traveling at or below light speed could get from one to the other. In this case, neither event can cause the other. They're independent. Now here's the crucial point. All observers in the universe must agree on the order of causally connected events. If you see event A cause event B, every other observer in the universe, no matter how fast they're moving, must also see A happen before B. Causality can't reverse. If it did, the universe would be inconsistent. Different observers would disagree about what caused what, and physics would be impossible. But here's where it gets interesting. Einstein's special relativity tells us that observers moving at different speeds disagree about when events happen. Time is relative. What looks simultaneous to one observer happens at different times to another observer moving at a different speed. Two events that you see as happening at exactly the same time might appear to someone else as happening seconds or even years apart, depending on how fast they're moving and where they are. This is called the relativity of simultaneity, and it's been verified by countless experiments. Time really is relative. There's no absolute universal clock. Now, combine these two facts. Observers must agree on the order of causally connected events, but observers disagree about when events happen. These two facts are only compatible if there's a maximum speed for cause and effect. If signals could travel infinitely fast, then everything could cause everything else, and different observers would disagree about the order of causation. The universe would be inconsistent. But if there's a maximum speed, a cosmic speed limit, then events can be divided into 3 categories. Events that can influence you, events that you can influence, and events that are causally disconnected from you. And this division is the same for all observers. Everyone agrees on which events can cause which other events, even though they disagree on the exact timing. The speed limit preserves causality. This is extraordinarily subtle, and it's worth spending time really understanding what's happening here. Think about it this way. You and I are in different places, moving at different speeds relative to each other. We each have our own perspective on when things happen. I see 2 events, and I say they happen at the same time. You see the same 2 events, and you say one happens before the other. We disagree about the timing, but we must agree on whether one event could have caused the other. If I see event A cause event B, you must also see A cause B, not B cause A. The causal order can't reverse. Now, imagine there's no speed limit. Imagine information can travel infinitely fast. In that case, any event anywhere in the universe could instantly affect any other event anywhere else. Everything could cause everything. There'd be no such thing as causally disconnected events. And if everything can cause everything, then different observers moving at different speeds would see different causal relationships. I might see event A cause event B, while you see event B cause event A. We'd both be right from our own perspectives, but the universe would be inconsistent. Physics would be impossible because different observers would disagree on the fundamental question of what causes what. The speed limit prevents this. If there's a maximum speed for signals, then not everything can affect everything else. Events that are far enough apart in space and close enough together in time are causally disconnected. Light from one event can't reach the other event in time to influence it. And this causal disconnection is the same for all observers. We might disagree on exactly when things happen, but we agree on whether light from event A could have reached event B. If it couldn't, then A didn't cause B, and every observer agrees on that. The speed limit creates a structure in spacetime that all observers agree on, even though they disagree on the specific timing. This structure is what makes physics possible. It's what allows us to have consistent laws that work the same way for everyone. Without it, the universe would be a chaotic mess where different observers saw completely different cause and effect relationships. Science would be impossible. Logic would be impossible. Reality itself would be impossible in any meaningful sense. So the speed of light isn't just a number. It's the fundamental organizing principle that makes the universe comprehensible. It's what allows cause and effect to work consistently. It's what prevents paradoxes and contradictions. It's what makes reality real. And this is why Feynman's argument is so powerful. He didn't just say that faster-than-light travel is impossible because the equations say so. He showed that faster-than-light travel would destroy the logical foundation of reality itself. Causality would break down. Time travel would be possible. Paradoxes would be everywhere. The universe would eat itself. The only way to have a consistent, comprehensible universe is if there's a maximum speed for information and causality. And that speed, whatever it is, must be the same for all observers, regardless of how fast they're moving. In our universe, that speed is approximately 300 million meters per second. We call it the speed of light because light travels at that speed, but it's really the speed of causality, the speed of information, the speed at which the universe operates. Let me give you another way to think about this. Imagine spacetime as a fabric, like a rubber sheet. Events are points on this sheet. Now, if there's no speed limit, then any point can instantly connect to any other point. The entire sheet is interconnected in an instant. But if there's a speed limit, then connections between points take time to form. A point here affects a point there, but only after enough time has passed for a signal to travel between them. This creates a structure, a pattern of connectivity. Close points are connected. Distant points aren't connected yet, but they will be once enough time passes. And this structure is what we call causality. It's the pattern of which events can influence which other events. The speed limit determines this pattern. It sets the rate at which causal influence spreads through space-time. And because the speed limit is the same for everyone, the causal structure is the same for everyone. We all agree on the pattern, even if we disagree on the specific coordinates of events. This is profound. It means that the speed of light is built into the deepest structure of space-time itself. It's not just a property of light, or of matter, or of energy. It's a property of space-time, of the arena in which all events occur. Space-time has a geometry, a shape, a structure, and that structure is determined by the speed limit. In mathematical terms, space-time is what's called a Lorentzian manifold. It's a four-dimensional space with three space dimensions and one time dimension, but they're not independent. They're linked together by the speed of light. The speed of light is the factor that converts between space and time, that tells you how much space corresponds to how much time. And this factor is invariant. It's the same for all observers. It's built into the metric, the mathematical object that describes distances and durations in spacetime. When Einstein formulated special relativity, he started with the principle that the speed of light must be constant for all observers. This was based on experimental evidence from the Michelson-Morley experiment, which showed that light travels at the same speed, regardless of Earth's motion through space. From this single principle, Einstein derived all the consequences of special relativity: time dilation, length contraction, the relativity of simultaneity, mass-energy equivalence. All of it follows from the constancy of the speed of light. But Feynman's argument shows us why the speed of light must be constant. It's not just an experimental fact. It's a logical necessity. If the speed of light weren't constant, if different observers measured different speeds for light, then causality would break down. The universe would be inconsistent. So the constancy of the speed of light is required by logic, and all the strange phenomena of relativity are consequences of this requirement. This is what makes relativity so beautiful. It's not a collection of arbitrary rules. It's a logical structure built on a single foundation. That foundation is the requirement that causality must work consistently for all observers. And from that single requirement, the entire theory follows. Let me make this concrete with Feynman's thought experiment. Imagine you have a spaceship that can travel faster than light. You're on Earth, and your friend is on Mars. You get on your faster-than-light spaceship and travel to Mars. From your perspective, you left Earth at noon and arrived on Mars at 1 p.m. 1 hour of travel time on your clock. But now, here's the trick. Your friend on Mars has been moving relative to Earth. Maybe Mars is moving away from Earth at half the speed of light. From your friend's perspective, they're stationary, and Earth is moving. And because of time dilation and the relativity of simultaneity, your friend sees events in a different order than you do. To your friend, you arrived on Mars at 1 p.m. local time, but you left Earth at 2 p.m. local time. You arrived before you left. From your friend's reference frame, the effect happened before the cause. Now, your friend gets on their own faster-than-light spaceship and travels back to Earth. From their perspective, they leave Mars at 2 p.m. and arrive on Earth at 3 p.m. But when they arrive on Earth, they find you still there because you haven't left yet. You don't leave until 2 p.m., which hasn't happened yet. They arrive back on Earth and meet you before you departed. This is a paradox. You traveled to Mars and your friend traveled back, but the two trips together form a loop in time. The effect precedes the cause. Information travels backward in time. You could give your past self information about the future, creating all sorts of contradictions. You could tell yourself not to go to Mars, but if you don't go to Mars, then your friend never comes back, and you never receive the message. So you do go to Mars, which means your friend does come back, which means you don't go, and on and on. The universe eats itself. Let's make this even more concrete, with specific numbers, to really drive the point home. Suppose you have a spaceship that can travel at twice the speed of light. That's 2 times c, or about 600 million meters per second. You leave Earth and head to a space station that's 1 light hour away. That's the distance light travels in 1 hour, about 621 million miles. From Earth's reference frame, you cover this distance in half an hour because you're going twice as fast as light. So you leave at noon Earth time and arrive at the space station at 12:30 p.m. Earth time. Simple enough. Now, here's where it gets weird. The space station is moving relative to Earth. Let's say it's moving at half the speed of light, in a direction perpendicular to your travel direction. This might seem like an arbitrary choice, but it doesn't matter which direction. The paradox occurs regardless. From the space station's reference frame, because of the relativity of simultaneity, events that Earth observers think are happening at the same time are actually happening at different times. When you left Earth at noon Earth time, the space station's clocks read something different. Because the space station is moving, it disagrees with Earth about what noon means. Due to the relativity of simultaneity, when Earth's clocks read noon, the space station's clocks might read 12:45 p.m. This is a real effect of special relativity. Moving observers disagree about simultaneity. So from the space station's perspective, you left Earth when their clocks read 12:45 p.m., but you arrived at the space station when their clocks read 12:15 p.m. You arrived 30 minutes before you left. The effect happened before the cause. Now, Let's say the space station immediately sends you back to Earth on their own faster-than-light ship, also traveling at twice the speed of light. From the space station's perspective, you leave at 12:15 p.m. and arrive back at Earth at 11:45 a.m. But 11:45 a.m. is 15 minutes before you originally left. You've traveled back in time by 15 minutes. You could meet yourself, tell yourself not to go, and create a paradox. This isn't science fiction speculation. This is what the mathematics of special relativity tells us would happen if faster-than-light travel were possible. The paradox is unavoidable. Any faster-than-light travel, in any direction, by any amount, allows you to construct these causal loops. And these loops destroy causality. They make it impossible for the universe to be consistent. The only way to avoid this is if nothing can travel faster than light. The speed limit isn't just a suggestion. It's an absolute requirement for the universe to make sense. Now, you might think there's a way around this. Maybe you could have some kind of absolute reference frame, some cosmic standard of rest, where everyone agrees on what time it is. Then the relativity of simultaneity wouldn't matter, and you could have faster-than-light travel without paradoxes. This is what physicists thought before special relativity. They believed in something called the luminiferous ether, a medium that filled all of space and through which light waves traveled. This ether would provide an absolute reference frame. If you were at rest, relative to the ether, you'd be truly at rest. Everyone could synchronize their clocks to ether time, and the relativity of simultaneity would go away. But the Michelson-Morley experiment in 1887 showed that the ether doesn't exist. They tried to measure Earth's motion through the ether by looking at how the speed of light changed depending on direction. If we were moving through the ether, light should travel faster in one direction than another, but they found no difference. Light traveled at the same speed in all directions, regardless of Earth's motion. The experiment was repeated many times with increasingly sophisticated equipment, and the result was always the same: no ether. The speed of light is the same for all observers, regardless of their motion. This was the experimental foundation for special relativity. Einstein took this result and built an entire theory around it. He showed that if the speed of light is constant for all observers, then time and space must be relative. Different observers must disagree about simultaneity, about duration, about distance. All of these things are consequences of the constancy of the speed of light. And if time and space are relative, then faster-than-light travel leads to time travel and paradoxes. There's no escape. The universe doesn't have an absolute reference frame. The ether doesn't exist. Time and space are relative. And therefore, the speed of light must be the universal speed limit. This is one of the great achievements of 20th century physics. Einstein didn't just discover a new law of nature. He revealed the structure of space-time itself. He showed that our intuitive notions of absolute time and absolute space were wrong. The universe is stranger and more subtle than we imagined. Time and space are interwoven into a single entity, space-time, and the speed of light is the fundamental constant that describes this entity's structure. Every subsequent experiment has confirmed this. Particle accelerators routinely accelerate particles to 99.9999% of the speed of light or higher. The closer particles get to light speed, the more energy is required to accelerate them further. The relationship follows exactly what Einstein's equations predict. No particle has ever been accelerated to the speed of light, let alone beyond it. The energy required grows without bound as you approach light speed, making it impossible to reach. Cosmic rays, high-energy particles from space, have been detected with energies far beyond what our accelerators can produce. Some cosmic rays have energies equivalent to macroscopic objects, like a baseball thrown at high speed, all concentrated in a single subatomic particle. These particles are traveling at speeds incredibly close to the speed of light, something like 99.999999999% of light speed. But they're still not quite at light speed, and they're certainly not faster. The closer they get to light speed, the more time dilation they experience. From our perspective, these particles take years to cross the galaxy. But from the particle's perspective, the journey is nearly instantaneous due to extreme time dilation. Space is contracted along their direction of motion, making the galaxy appear much thinner than it does to us. But even with these extreme effects, the particle never quite reaches light speed. The universe enforces the limit, absolutely. Atomic clocks on satellites in orbit tick at different rates than identical clocks on Earth's surface, exactly as relativity predicts. GPS satellites have to correct for these relativistic effects, or their position calculations would be off by many miles. Every time you use GPS, you're relying on Einstein's equations being correct. The system wouldn't work if relativity were wrong. Gravitational waves, ripples in spacetime itself, have been detected by LIGO and other observatories. These waves travel at exactly the speed of light, as general relativity predicts. Not faster, not slower, but exactly at c. The universe is telling us, over and over again, that the speed of light is special. It's not just the speed at which light happens to travel, it's the maximum speed built into the structure of spacetime itself. And Feynman's argument tells us why it must be this way. Without a speed limit, causality breaks down. With a speed limit, the universe is consistent, comprehensible, and governed by laws that work the same way for all observers. The speed limit is what makes physics possible. It's what makes science possible. It's what makes the universe make sense. This isn't just a weird edge case. Any faster than light travel in any reference frame allows you to construct these causal loops. Cause and effect breaks down. The universe becomes logically inconsistent. Feynman's point is that the universe can't allow this. Causality must be preserved. Effects must follow causes. And the only way to guarantee this is if there's a maximum speed for information, energy, and matter. A speed that's the same for all observers, regardless of how fast they're moving. That speed is the speed of light. Nothing can exceed it, because exceeding it would destroy causality itself. The math of special relativity bears this out. When you try to accelerate an object, you have to add energy. The faster the object is moving, the more energy you need to add to make it go a little faster. As you approach the speed of light, the amount of energy required to accelerate further grows without bound. To actually reach the speed of light would require infinite energy, which is impossible, and to exceed the speed of light would require more than infinite energy, which is nonsensical. The equations literally forbid it. But the equations are just describing the underlying reality that Feynman explained. Causality requires a speed limit. The universe must have a maximum speed for signals and matter. And that speed, built into the geometry of space-time itself, is what we call the speed of light. Now, you might wonder about particles that already travel at light speed. Photons, the particles of light, travel at exactly 300 million meters per second. They don't accelerate up to that speed. They're created already, moving at light speed, and they can never slow down or speed up. They're always moving at exactly light speed in all reference frames. This seems strange until you realize that photons have zero mass. Massless particles must travel at the universal speed limit. They have no choice. The equations of special relativity say that anything with zero mass must move at exactly the speed of light, and anything with mass must move slower than light. There's no middle ground. You're either massless and moving at light speed, or you have mass and you're moving slower. This creates a fundamental divide in the universe. There are two types of particles. Massive particles, which can exist at rest and must travel slower than light, and massless particles, which can never be at rest and must always travel at exactly light speed. Nothing can transition from one category to the other. A massive particle can't speed up to light speed because doing so would require infinite energy. A massless particle can't slow down from light speed because it has no rest mass to slow down to. The two categories are fundamentally separate. This might seem like a strange dichotomy, but it's a direct consequence of the structure of spacetime. The speed of light isn't just the maximum speed. It's a dividing line that separates different types of existence. Massive particles experience time. They have a history, a past, present, and future. They can accelerate, decelerate, change direction. They have an inertia, a resistance to changes in motion, because they have mass. Massless particles don't experience time at all. From their perspective, if such a thing makes sense, they're created and destroyed in the same instant. They don't have a history. They're never at rest, never stationary, always moving at exactly light speed. This raises an interesting question. What would it be like to be a photon? From the photon's perspective, what does the universe look like? The answer is deeply strange. Because of time dilation, time slows down as you approach light speed. The faster you go, the slower time passes for you relative to stationary observers. At 99% of light speed, time passes about 7 times slower for you than for someone standing still. At 99.9% of light speed, time passes about 22 times slower. At 99.99%, about 70 times slower, the pattern continues. At 99.9999% of light speed, time passes about 700 times slower. At 99.999999%, about 7,000 times slower. As you approach light speed, time dilation increases without limit. It approaches infinity. And at exactly light speed, time dilation becomes infinite. From a photon's perspective, time doesn't pass at all. A photon emitted from a star travels across the galaxy for thousands of years from our perspective. But from the photon's perspective, the journey is instantaneous. It's emitted and absorbed in the same instant. No time passes. The photon doesn't experience duration. It doesn't age, doesn't decay, doesn't change. The entire universe, from the photon's point of view, is compressed into a single instant of existence. This is what it means to travel at light speed. You don't experience time, and not experiencing time means you can't have thoughts, can't have experiences, can't have any kind of subjective existence. Existence requires change, and change requires time. Without time, there's no such thing as experience. So photons don't experience anything. They're not conscious. They don't have a perspective in any meaningful sense. But mathematically, we can ask what the universe looks like from a photon's reference frame, even if that frame is physically impossible for anything that experiences time. And the answer is that distance along the direction of motion is contracted to zero. This is called length contraction, another effect of special relativity. As you move faster, distances along your direction of motion appear to shrink. At 99% of light speed, distances shrink to about 14% of their normal length. At 99.9%, they shrink to about 4%. At 99.99%, to about 1.4%. The pattern continues as you approach light speed. And at exactly light speed, the contraction is infinite. All distances along the direction of motion become zero. From a photon's perspective, the entire universe in the direction it's traveling is compressed into a single point. A photon traveling from one side of the galaxy to the other crosses a distance of 100,000 light-years from our perspective. But from the photon's perspective, there's no distance at all. The starting point and ending point are at the same location. The journey is instantaneous because there's no distance to traverse and no time in which to traverse it. This is the ultimate consequence of approaching light speed. Space and time themselves transform in such extreme ways that the normal concepts of distance and duration cease to make sense. This is what it means to travel at light speed. You don't experience time. You don't cross distances. Cause and effect, duration, change. All of these concepts require time to flow, and at light speed, time doesn't flow. This is another way to see why nothing with mass can reach light speed. You exist in time. You experience duration. You change from one moment to the next. Your thoughts occur in sequence. Your heart beats, your cells divide, your atoms vibrate. All of this requires time. For you to reach light speed would require you to exit time entirely, which doesn't make sense for something that exists and changes. You would have to become timeless, experienceless, unchanging. You would have to stop being a thing that exists in the normal sense. Only massless particles, which don't experience time to begin with, can travel at this ultimate speed. And even then, it's not clear that we should think of photons as experiencing anything. They don't have a subjective existence. They're not aware. They're just excitations in the electromagnetic field, propagating at the speed determined by the structure of spacetime. But there are other massless particles besides photons. Gluons, the particles that mediate the strong nuclear force, are also massless. They travel at light speed. Gravitons, if they exist, would be the particles that mediate gravity. They would also be massless and travel at light speed. We haven't directly detected gravitons yet, because gravity is such a weak force that individual graviton interactions are almost impossible to measure. But gravitational waves, which would be made of many gravitons, travel at exactly light speed, as we've observed. There might be other massless particles we haven't discovered yet, or there might not be. The universe might only have a few types of massless particles. But however many there are, they all travel at exactly the same speed, the speed of light, not because they're trying to, but because they have no choice. Massless particles must move at the universal speed limit built into spacetime. There's also an interesting question about whether neutrinos are massless or not. For many years, physicists thought neutrinos were massless. They're produced in nuclear reactions, like those in the sun's core, and they barely interact with matter. Trillions of neutrinos from the sun pass through your body every second, and they almost never interact with your atoms. They just pass straight through as if you weren't there. Because neutrinos interact so weakly, they're very hard to detect, and for a long time, we couldn't measure their properties precisely enough to determine whether they had mass. The assumption was that they were massless like photons, traveling at exactly light speed. But in the late 1990s and early 2000s, experiments showed that neutrinos oscillate. They change from one type to another as they travel. Electron neutrinos can turn into muon neutrinos, which can turn into tau neutrinos, which can turn back into electron neutrinos. This oscillation can only happen if neutrinos have mass. Massless particles can't oscillate between different types, so we now know that neutrinos have mass, even though the mass is incredibly tiny. The exact mass isn't known yet, but it's at least millions of times smaller than the mass of an electron, which is already incredibly small. Because neutrinos have mass, they must travel slower than light, even if only slightly slower. They can't quite reach light speed, but they're traveling so fast, so close to light speed, that the difference is almost impossible to measure. When a supernova exploded in 1987, producing supernova 1987A, we detected neutrinos from the explosion. They arrived at Earth within hours of the light from the supernova, even though the supernova was about 160,000 light-years away. The neutrinos and the light traveled for 160,000 years to reach us, and they arrived within hours of each other. This tells us that neutrinos travel at almost exactly the speed of light. They're just barely slower, by an amount so small that over 160,000 light-years, they only fall behind by a few hours. This gives us an upper limit on neutrino mass. If they had more mass, they'd travel slower, and they would have arrived days or weeks after the light, not just hours. So we know neutrinos are very light, traveling very close to light speed, but not quite at it. They're massive particles, not massless ones, so they must obey the speed limit. This distinction between massive and massless particles is fundamental to how the universe works. It's built into the equations of quantum field theory, the framework that describes all known particles and forces. In quantum field theory, particles are excitations of fields that permeate all of space. The electromagnetic field gives rise to photons. The electron field gives rise to electrons. The quark fields give rise to quarks, and so on for all the known particles. Each field has properties that determine whether its particles have mass or not. Particles with mass have a rest energy, an energy they possess even when not moving. This rest energy is given by Einstein's famous equation, E equals mc squared. The mass m is the rest mass, and c squared is the speed of light squared, the conversion factor between mass and energy. Massless particles have no rest energy. All their energy is kinetic energy, energy of motion. They must always be moving, and they must always move at light speed. The distinction is fundamental and built into the very structure of quantum field theory. It's not something that can change or be violated. It's a consequence of how fields and particles work in our universe, and it all traces back to the structure of space-time and the universal speed limit we call the speed of light. Now, let's talk about what the speed limit means for the structure of the universe. The speed of light is finite, which means the universe has a kind of fundamental graininess to how fast things can happen. Information takes time to travel. When you look at a star, you're not seeing it as it is right now. You're seeing it as it was when the light left it. Proxima Centauri, the nearest star to our Sun, is 4.24 light-years away. When you look at it, you're seeing light that left that star 4.24 years ago. You're looking 4 years into the past. If Proxima Centauri exploded right now, we wouldn't know for 4.24 years. The information about the explosion would travel toward us at light speed, and it would take over 4 years to reach us. During those 4 years, from our perspective, Proxima Centauri still exists. We'd see it shining in the sky, completely unaware that it's actually gone. The star could be destroyed, but the information about its destruction hasn't reached us yet. In a very real sense, from our reference frame, the star still exists, because existence and information are connected. If we have no way of knowing something happened, then in our causal past, it hasn't happened. Different parts of the universe exist in different time periods from each other. The present moment isn't a single universal instant. It's different for every location in space, depending on how far away that location is and how fast it's moving relative to you. This is one of the most profound and counterintuitive consequences of special relativity. We're used to thinking of now as meaning the same thing everywhere. We think that when it's noon here, it's noon everywhere in the universe, at least in some absolute sense. Maybe we have to account for time zones or the distance light travels, but we think there's an absolute present moment that's the same for everyone. Special relativity tells us this is wrong. There's no universal present moment. Different observers define the present differently. Two events that are simultaneous for one observer happen at different times for another observer moving at a different speed. This is called the relativity of simultaneity, and it's a direct consequence of the constancy of the speed of light. Let me give you an example. Imagine a train moving past a platform. There's an observer on the train and an observer on the platform. Lightning strikes both ends of the train simultaneously from the platform observer's perspective. The platform observer sees both flashes at the same time, but the train observer is moving toward one lightning strike and away from the other. So the light from the front of the train reaches the train observer before the light from the back. From the train observer's perspective, the lightning strike at the front happened first, and the lightning strike at the back happened later. The two observers disagree about whether the events were simultaneous, and both observers are right from their own perspectives. There's no absolute truth about whether the events happened at the same time or not. The answer depends on your reference frame. This sounds like just a curiosity, a weird quirk of relativity, but it has profound implications. It means that you can't point to a distant galaxy and say what's happening there right now. The question doesn't have a unique answer. What's happening now depends on your reference frame. An observer moving at a different speed would give a different answer about what's happening in that galaxy at this moment. The universe doesn't have a single present moment that everyone agrees on. It has many different presents, one for each possible reference frame, and all of them are equally valid. This leads to something called the light cone structure of spacetime. Imagine yourself at a particular moment in space and time. Let's call this moment now, and this location here. Your spacetime coordinates are this particular point in four-dimensional spacetime. Now, think about all the events in the universe that could have influenced you. These are events that happened in the past, and close enough that light from them could have reached you by now. An event that happened 1 billion years ago and 1 billion light years away could have influenced you because light from that event has had just enough time to reach you. An event that happened 1 billion years ago but 2 billion light years away couldn't have influenced you because light from that event hasn't had enough time to reach you yet. The light is still traveling, still on its way, but it hasn't arrived. The set of all events that could have influenced you forms a cone shape in space-time. This is your past light cone. It's the surface defined by light rays converging on your location from all directions. If you draw a space-time diagram with time as the vertical axis and space as the horizontal axis, the past light cone looks like a cone opening downward into the past. The tip of the cone is you, here and now. The surface of the cone is all the events from which light could have just barely reached you. The interior of the cone is all the events from which light could easily have reached you, with time to spare. Everything inside this cone could have affected you. Events inside the cone are in your causal past. They could have sent signals to you, influenced your present state, caused things to happen that you're experiencing now. Everything outside the cone couldn't have affected you because light from those events hasn't reached you yet. Those events are not in your causal past. They exist, or they will exist, or they have existed, depending on the reference frame, but they haven't had the opportunity to influence you yet. Similarly, there's a future light cone. These are all the events that you could possibly influence. If you send a signal right now, traveling at light speed or slower, it will reach certain events and not others. Events inside your future light cone can be influenced by you. Events outside your future light cone cannot be influenced by you because no signal you send could reach them yet. The future light cone is like the past light cone but opening upward into the future instead of downward into the past. The surface of the future light cone represents light rays diverging from your location in all directions. The interior represents events you could influence by sending signals slower than light. The exterior represents events that are too far away for you to influence yet. Between the past light cone and the future light cone is a region called elsewhere. These are events that are happening right now, but too far away for light to have traveled between them and you. You can't influence them, and they can't influence you, at least not yet. In the future, as more time passes, some of these events will enter your future light cone, meaning you could start to influence them, and some will enter your past light cone, meaning they could start to influence you. But right now, they're causally disconnected from you. In a very real sense, these events are not part of your causal universe. They exist, but they're not accessible to you. You could define your present moment to include some of them if you choose a particular reference frame, but other observers would choose different events. There's no unique answer to what's happening right now at a location in the elsewhere region. This structure, the light cone structure, is fundamental to how the universe works. It's a direct consequence of the finite speed of light, and it means that the universe doesn't have a single universal present moment. Different observers define the present differently, and events that are in one observer's past might be in another observer's future if those events are far enough apart in space. But here's the key point. All observers agree on the light cone structure. Everyone agrees on which events are in the past light cone, which are in the future light cone, and which are elsewhere. The boundaries of these regions are defined by light rays, which travel at the same speed for all observers. So, even though different observers disagree about when things happen, they all agree on the causal structure of space-time. They all agree on which events could cause which other events. This is what makes physics possible. This is what makes science possible. We can disagree about timing, about simultaneity, about how much time passes between events, but we all agree on the fundamental question of what can cause what, and that agreement is guaranteed by the universal speed limit. The light cone structure also tells us something important about the nature of space-time itself. Space-time isn't just space and time as separate things. It's a unified four-dimensional entity with a particular geometry. The light cones define this geometry. They tell us how space-time is structured, how it connects events to each other, how causality flows from past to future. In flat space-time, the space-time of special relativity with no gravity, the light cones are simple and symmetric. They open at a 45-degree angle if you use units where the speed of light equals 1. Every event has the same light cone structure. The geometry is the same everywhere. But in curved space-time, the space-time of general relativity with gravity, the light cones can tilt and warp. Near a massive object like a star or a black hole, the curvature of space-time causes the light cones to tilt. Events that would be elsewhere in flat space-time might be in the future light cone in curved space-time. The geometry is different. Near a black hole, the curvature becomes so extreme that inside the event horizon, the future light cone points toward the singularity at the center. All possible future paths, all time-like trajectories, lead to the singularity. You can't escape because escaping would require traveling faster than light, which is impossible. The light cone structure determines your fate. Once you're inside the event horizon, your future light cone is entirely interior to the black hole. There's no possible future for you that doesn't involve hitting the singularity, not because you're being pulled by a force, but because the geometry of space-time itself has been warped so severely that all future directed paths lead inward. The speed limit, combined with the curvature of space-time, traps you. This is the power of general relativity. It describes gravity not as a force, but as the curvature of space-time. And that curvature affects the light cone structure, changing which events can influence which other events. But even in curved space-time, even near black holes, or in the extreme conditions of the early universe, the speed of light remains constant. Locally, at any particular point in space-time, light travels at exactly 300 million meters per second. The global structure might be complicated, the light cones might tilt and warp, but locally, light always travels at the same speed. This is a fundamental principle of general relativity. It's called the equivalence principle, and it states that locally, in a small enough region of space-time, the laws of physics are the same as in special relativity. Gravity might curve space-time on large scales, but on small scales, locally, space-time looks flat, and light travels at its usual speed. This principle is what allowed Einstein to extend special relativity to general relativity. He demanded that the theory must reduce to special relativity in the limit of no gravity, in regions where space-time is flat. And because special relativity requires the speed of light to be constant, general relativity also requires it. The speed limit is preserved, even when gravity is included, so the light cone structure, the causal structure of space-time, is fundamental. It's the same for all observers, even though they might disagree about other things. It's preserved even in curved space-time, even in the presence of gravity, and it all stems from the simple fact that there's a universal speed limit built into the structure of space-time itself. This speed limit determines how events can influence each other, how causality flows, how the universe evolves from one moment to the next. Without it, space-time wouldn't have a consistent structure. Causality would break down. The universe wouldn't make sense. The speed of light isn't just a number. It's the fundamental constant that makes the universe comprehensible. Einstein realized all of this in 1905 when he published his special theory of relativity. He showed that the speed of light is the same for all observers, regardless of how fast they're moving. This sounds impossible at first. If you're on a train moving at 100 miles per hour and you throw a ball forward at 50 miles per hour, someone standing on the ground sees the ball moving at 150 miles per hour. The speeds add, but light doesn't work this way. If you're on a spaceship moving at half the speed of light and you turn on a flashlight, the light from the flashlight doesn't travel at 1.5 times the speed of light. It travels at exactly the speed of light, the same as it would if you were standing still. This seems to violate common sense. How can light always travel at the same speed regardless of how fast the source is moving? The answer is that time and space themselves adjust to make this true. When you're moving fast, time slows down for you, and distances contract. These effects exactly compensate so that light always travels at the same speed in your reference frame. This isn't an illusion or a trick of measurement. Time really does slow down, and space really does contract. These are physical changes to the fabric of reality, and they've been verified by countless experiments. Atomic clocks on airplanes tick slower than atomic clocks on the ground. Particles moving near light speed live longer before decaying than particles at rest. GPS satellites have to account for time dilation, or their position calculations would be off by many miles. The evidence is overwhelming. Special relativity is correct, and it requires the speed of light to be a universal constant. But Einstein didn't stop there. In 1915, he published his general theory of relativity, which extended these ideas to include gravity. In general relativity, gravity isn't a force. It's a curvature of space-time caused by mass and energy. Massive objects like stars and planets warp the fabric of space-time around them, and other objects move along the curves in this warped space-time. We perceive this motion as being pulled by gravity, but really, the objects are just following the straightest possible paths through curved space-time. And here's the key point for our story. In general relativity, the speed of light is still the universal speed limit. It's still the maximum speed at which information can travel. But now, space-time itself can curve and warp, which complicates things. Light always travels at 300 million meters per second through space, but space itself can be curved, stretched, or compressed. This means that the effective speed of light can appear different in different situations. Near a black hole, for example, space-time is so severely curved that light can take longer to escape from the strong gravitational field. From far away, it looks like light is moving slower near the black hole. But locally, at any particular point, light is always moving at exactly the speed of light through the spacetime at that point. The spacetime itself is just curved. Another consequence of general relativity is that the universe itself is expanding. The space between galaxies is stretching, and this stretching can carry galaxies away from each other faster than the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. The space between them is expanding. It's a subtle distinction, but it's important. The speed of light is the limit for how fast things can move through space, but it doesn't limit how fast space itself can expand. Right now, there are galaxies moving away from us so fast that light from them will never reach us. The expansion of space is carrying them away faster than their light can travel toward us. These galaxies are beyond our cosmic horizon, forever inaccessible. We'll never see them, never communicate with them, never visit them. They exist, but they're not part of our causal universe. This is another manifestation of the speed limit. The finite speed of light combined with the expansion of space means that there are parts of the universe we can never interact with. Our observable universe is limited by how far light can travel since the Big Bang. Beyond that distance, we simply can't see. Now, let's talk about some of the practical implications of the speed of light being finite. For everyday life on Earth, the speed of light seems instantaneous. Light travels around the Earth 7.5 times in 1 second. If you turn on a light switch, the light reaches your eyes in a few nanoseconds. You don't notice any delay. When you have a video call with someone on the other side of the planet, the signal travels through fiber optic cables and satellites. Even accounting for routing and switching delays, the signal travels at a significant fraction of light speed. The delay is usually less than a second, barely noticeable in conversation. You might experience a slight lag, but it doesn't fundamentally change how communication works. You can still have a real-time conversation, but once you start dealing with astronomical distances, the delays become significant. The Moon is about 1.3 light seconds away. That's the distance light travels in 1.3 seconds, approximately 239,000 miles. When you look at the Moon, you're seeing it as it was 1.3 seconds ago. If the Moon exploded right now, you wouldn't see the explosion for 1.3 seconds. During those 1.3 seconds, from your perspective, the Moon still exists, still shines in the sky. The information about its destruction is traveling toward you at light speed, but it hasn't arrived yet. This delay was noticeable during the Apollo missions. When astronauts on the Moon sent a radio signal to Earth, there was a 2.6-second round-trip delay. The astronauts would say something, and it would take 1.3 seconds for the signal to reach Earth. Mission Control would respond, and it would take another 1.3 seconds for the response to reach the Moon. So there was always at least a 2.6-second pause in the conversation. The astronauts would ask a question, wait, and then hear the answer. Mission Control would hear a question, wait, and then send an answer. Every exchange had this awkward pause built in. It was like talking to someone with a bad phone connection, except the delay was unavoidable, built into the physics of the universe. No amount of technology could eliminate it. You can't make radio waves travel faster than light. This is just how fast information propagates through space. The Sun is 8 light minutes away. That's about 93 million miles. Light takes 8 minutes and 20 seconds to travel from the Sun to Earth. When you look at the Sun, you're seeing it as it was 8 minutes ago. You're not seeing the Sun as it is right now, in this present moment. You're seeing the Sun as it was when the light left the Sun's surface 8 minutes ago. If the Sun suddenly vanished right now, we wouldn't know for 8 minutes. For 8 minutes, we'd continue to see the Sun shining in the sky. Earth would continue to orbit the Sun for 8 minutes, because the gravitational influence of the Sun also travels at the speed of light. Gravity isn't instantaneous. Changes in the gravitational field propagate at light speed, so if the Sun disappeared, its gravitational pull on Earth would also disappear, but not instantly. The change would propagate outward as a gravitational wave traveling at light speed. 8 minutes after the Sun vanished, the gravitational wave would reach Earth, and Earth would suddenly fly off in a straight line, no longer held in orbit. At that same moment, 8 minutes after the Sun vanished, the Sun would disappear from the sky. We'd lose the Sun's light and the Sun's gravity simultaneously, 8 minutes after the Sun actually ceased to exist. This is the reality of living in a universe with a finite speed limit. Events that happen far away don't affect us instantly. There's always a delay, a light travel time, between when something happens and when we can know about it or be affected by it. Mars, at its closest approach to Earth, is about 3 light minutes away. That's about 34 million miles. At its farthest, when Mars and Earth are on opposite sides of the Sun, Mars is about 22 light minutes away, approximately 250 million miles. The distance varies because both planets are orbiting the Sun, sometimes coming closer together and sometimes moving farther apart. On average, Mars is about 12 light minutes away. This creates significant challenges for missions to Mars. Rovers on Mars, like Curiosity or Perseverance, receive commands from Earth with a significant time delay. If Mars is 10 light minutes away, a round-trip communication takes 20 minutes. Engineers on Earth send a command. 10 minutes later, the command reaches Mars. The rover executes the command. 10 minutes later, confirmation reaches Earth. 20 minutes have passed for a single exchange of information. This makes real-time control impossible. Engineers can't drive the rover with a joystick the way you might control a remote control car. By the time they see what the rover's camera is showing, the image is 10 minutes old. If they try to steer around an obstacle, the command takes 10 minutes to arrive, and by then, the situation might have changed. The rover might have already hit the obstacle or moved past it. Real-time control just doesn't work with these delays. Instead, the rovers have to be largely autonomous. Engineers send a series of commands. Drive forward 2 meters, turn left 20 degrees, take a photo, analyze this rock. The rover executes these commands on its own, using its onboard computers and sensors to avoid obstacles and handle unexpected situations. Hours or even days later, the rover sends back data about what it did, and engineers evaluate the results and send new commands. It's a slow, patient process. A journey that would take minutes with real-time control takes days or weeks because of the communication delay. This is one of the major challenges of space exploration. The farther you go, the longer the delays, and the more autonomous your spacecraft must be. Jupiter is about 40 light minutes away, on average. A round-trip signal to Jupiter takes about 80 minutes. Saturn is about 80 light minutes away, so a round trip takes about 160 minutes, nearly 3 hours. When the Cassini spacecraft was orbiting Saturn, every command from Earth took 80 minutes to arrive, and every response from Cassini took 80 minutes to get back. Engineers had to plan everything far in advance, anticipating problems and programming Cassini to handle them autonomously. Uranus is about 160 light minutes away, almost 3 hours. Neptune is about 250 light minutes away, over 4 hours. A round-trip signal to Neptune takes 8 to 9 hours. If something goes wrong with a spacecraft at Neptune, Earth won't know for 4 hours, and any fix we send won't arrive for another 4 hours. By the time the fix arrives, 8 hours have passed, and the situation has likely changed completely. Voyager 1, the most distant human-made object, is currently over 15 billion miles away, which is about 22 light hours. It takes more than 22 hours for a signal from Voyager to reach Earth, and another 22 hours for any command from Earth to reach Voyager. A round-trip communication takes nearly 2 full days. If something went wrong with Voyager right now, we wouldn't know for almost a full day, and if we wanted to send a command to fix it, the command wouldn't arrive for another full day. By the time the command arrived, 2 days would have passed. At that distance, with that delay, real-time control is completely meaningless. Voyager is essentially on its own, coasting through interstellar space, sending back data when it can, but operating autonomously, because there's no other choice. The nearest star system, Alpha Centauri, is 4.37 light-years away. That's about 25 trillion miles. If we wanted to send a message to someone there, assuming anyone is there to receive it, the message would take 4.37 years to arrive. If they responded immediately, the response would take another 4.37 years to come back. A single exchange of information would take 8.74 years. Almost 9 years for one question and one answer. By the time you got a reply, you might have forgotten what you asked. The situation you asked about would have changed completely. Any conversation would be painfully, impossibly slow. You'd send a message saying, "Hello, we exist, we come in peace." 4.37 years later, your message arrives. If they respond immediately, 4.37 years after that, you receive their reply. 9 years after you sent your greeting, you finally hear back. In those 9 years, governments could rise and fall. Technologies could be invented and become obsolete. People could be born, grow up, and graduate from high school. And you're still waiting for a single reply to a single message. Any kind of real-time communication, the kind of immediate back-and-forth conversation we take for granted, is completely impossible across interstellar distances. Conversations would span decades. Debates would take centuries. A diplomatic negotiation between Earth and a colony at Alpha Centauri could take 100 years or more to resolve, with each party carefully considering their responses, knowing that years would pass before hearing back. This has profound implications for governance and society that go far beyond just inconvenience. A colony 4 light-years away couldn't be governed from Earth in any meaningful sense. Laws and directives sent from Earth would arrive years out of date. The political situation on Earth could change completely between when a message was sent and when it arrived. By the time the colony receives orders from Earth, those orders might be obsolete, overturned by new governments or new policies. The colony would need to be autonomous, capable of making its own decisions on everything from resource allocation to conflict resolution to emergency response, because waiting years for approval or guidance on every decision would be impossible. The colony couldn't function if it had to wait years for every decision to be approved by Earth. By the time approval arrived, the situation would have changed, the opportunity would be lost, or the problem would have resolved itself one way or another. The colony would have to make its own laws, establish its own government, develop its own culture and customs. It would be independent, not by choice, but by necessity. The speed of light would enforce that independence. The colony and Earth would drift apart culturally over time, developing their own customs, their own ways of life, their own solutions to problems. They'd be connected by messages from the past, letters from another time, but unable to maintain the kind of immediate, ongoing connection that holds societies together. The colonists would grow up hearing stories about Earth, seeing recordings sent years ago, but never experiencing Earth directly. Earth would be a distant memory, a place their grandparents came from, not a living connection. Over generations, the colony and Earth might become so different that they'd barely recognize each other anymore. They'd share a common origin, a common history up to the point of separation, but from that point forward, they'd diverge. They'd evolve separately, like species isolated on different islands. Common ancestors, but increasingly different adaptations to different environments. For more distant stars, it gets even worse. A settlement 10 light-years away would have a 20-year round-trip communication time. Messages you send to your children living there would reach them when they're adults, possibly with children of their own. Their responses would return when your grandchildren are grown, when you're old or possibly dead. You'd exchange letters across the decades, like messages from different eras. You could share news and stay in touch in some abstract sense, but you couldn't have a relationship in any normal meaning of the word. You couldn't give advice when it's needed, because the advice would arrive decades too late. You couldn't comfort them in times of trouble, because by the time your comfort arrived, the trouble would be long past. You'd be communicating with your future self, in a sense, sending messages to a person who will exist decades from now, in a world you can barely imagine. A civilization 100 light-years away would have a 200-year communication delay. You could send a message, and neither you nor your children nor your grandchildren nor even your great-grandchildren would live to see the reply. Only your great-great-great-grandchildren, living in a world you could barely imagine, might hear back from the distant civilization. The conversation would span generations. Each generation sending messages to strangers they'd never meet, receiving messages from people long dead, people separated not just by distance but by time, receiving messages from people who lived and died centuries ago. If you received a message from a civilization 100 light-years away, you'd be hearing from people who lived 100 years ago. By the time you receive their message, they might all be dead. Their civilization might have collapsed, been destroyed, or evolved into something completely different. You'd be hearing voices from the past, not the present. And if you responded, your response would reach them 100 years in the future, if they still exist, if they're still listening. This creates a picture of a universe that might be full of life, perhaps even intelligent life, but where that life is forever isolated by the vast distances of space and the finite speed of light. Each civilization develops alone, asks its questions alone, makes its discoveries alone, and eventually dies alone, never knowing if anyone else was out there, never making meaningful contact with other minds under other suns. There's something melancholy about this. We've evolved as social creatures. Connection with others is fundamental to who we are as humans. We build communities, share knowledge, collaborate on projects, draw meaning from our relationships with others. The idea of being alone in the universe, or of being surrounded by others but forever unable to reach them or communicate with them meaningfully, is profoundly isolating. It suggests that no matter how far we spread, no matter how many worlds we settle, we'll always be fundamentally isolated from other species, other civilizations, other forms of intelligence. We might find evidence that they exist, detect their radio signals, see the lights of their cities, but we'll never have a conversation with them. We'll never exchange ideas in real time, never collaborate on projects, never truly connect. We'll be neighbors in space, but strangers in time, our messages crossing in the void, arriving decades or centuries after they were sent, replies to questions we've forgotten, answers to problems we've already solved or failed to solve on our own. But there's also something beautiful about this realization. It means every civilization that does arise is precious. If we're alone, or effectively alone because we can't meaningfully reach anyone else, then we carry a unique responsibility. We're the universe's way of knowing itself in this particular corner of space. The thoughts we think, the art we create, the science we discover, the love we feel, the compassion we show, all of it is unique to us. We're not just one civilization among millions in constant communication. We might be the only minds in our region of space, the only consciousness for dozens or hundreds of light years in any direction. This makes what we do matter more, not less. Every act of kindness, every discovery, every work of art, every moment of joy or connection or understanding, it all matters because it's happening here and now and might not be happening anywhere else nearby. We're alone, but we're also important. We're small on cosmic scales, but we're also precious, irreplaceable. We're insignificant in the grand scheme of things, but we're also unique because there might not be anyone else like us for light years in any direction. The speed of light isolates us, yes, but it also gives us responsibility. We're not just observers of the universe. We're participants, conscious beings capable of understanding and appreciating the cosmos. And if we're alone in that, if there's no one else nearby to share the burden or the joy, then what we do matters all the more. We have to be kind to each other because there's no one else. We have to preserve our knowledge because there's no one else to remember it. We have to take care of our planet because it might be the only place in the galaxy where life has arisen, where consciousness has emerged, where the universe has become aware of itself. This puts severe constraints on interstellar communication and travel. Even if we could build a spaceship that traveled at a significant fraction of light speed, say 10%, it would still take 43 years to reach Alpha Centauri. The people who left Earth would arrive middle-aged or elderly, having spent their entire adult lives in transit, and messages back to Earth would arrive decades after being sent, long after the situations they described had changed. But let's think more carefully about what interstellar travel would actually involve. Suppose we could build a spaceship capable of reaching 10% of light speed. That's 30 million meters per second, 100 times faster than anything humans have ever built. The fastest spacecraft we've ever launched, the Parker Solar Probe, reaches about 118 miles per second at its closest approach to the Sun, which is about 0.06% of light speed. So we're talking about a spacecraft more than 150 times faster than our current best. This would require enormous amounts of energy and revolutionary propulsion technology. But let's assume we solve those problems and build this ship. The journey to Alpha Centauri would take 43 years. The crew would age 43 years during the journey. They'd need life support systems that could function reliably for over 4 decades. They'd need food, water, air, power, all sustained for 43 years without resupply. They'd need to protect themselves from radiation, from micrometeorite impacts, from equipment failures, from medical emergencies. They'd need to maintain their mental health despite being confined to a small spacecraft for decades, with no possibility of turning back, no possibility of outside help, knowing that everyone they knew on Earth would be 43 years older or dead by the time they arrived. And that's at 10% of light speed. At 1% of light speed, which would be much easier to achieve technologically, the journey would take 437 years. Everyone who left would be dead long before arrival. It would be a multi-generational mission, with children and grandchildren and great-grandchildren born on the ship, living their entire lives in space, arriving at a destination their ancestors left centuries ago. The people who arrived wouldn't remember Earth except through stories and recordings. They'd be space-born, raised in artificial gravity, adapted to life on a spacecraft. Would they even want to colonize a planet when they arrived? Would planetary gravity feel oppressive to people who grew up in the controlled environment of a spaceship? These are real questions that any interstellar mission would have to address. The challenges aren't just technological, they're biological, psychological, sociological. You're not just sending people to another star, you're creating a new branch of humanity that will evolve separately for centuries. Now, there's a twist here related to special relativity, that makes things slightly less bleak for the travelers, though not for the people back home. If you travel at a significant fraction of light speed, you experience time dilation. Time passes more slowly for you than for people who stayed behind. At 10% of light speed, the effect is small, only about 0.5%. You'd age about 42.8 years, while Earth aged 43 years. Barely noticeable. But at higher speeds, the effect becomes dramatic. At 50% of light speed, time dilation becomes significant. For every year that passes on Earth, you experience only about 8 months. A journey to Alpha Centauri at half-light speed would take 8.7 years, according to Earth's clocks. But from your perspective on the ship, only about 7.5 years would pass. You'd arrive younger than if you'd stayed on Earth. At 90% of light speed, the effect is much larger. Time dilation is about 2.3 to 1. For every year on Earth, you experience only about 5 months. The journey to Alpha Centauri would take about 4.9 years, according to Earth, but only about 2.1 years from your perspective on the ship. You'd experience only 2 years of aging during a journey that takes Earth nearly 5 years. At 99% of light speed, time dilation is about 7 to 1. The journey takes about 4.4 years, according to Earth, but only about 7 months from your perspective. You'd age only 7 months during a journey that takes Earth over 4 years. This is real, verified by countless experiments with particles in accelerators and atomic clocks on aircraft. Time really does slow down at high speeds. At 99.9% of light speed, time dilation is about 22 to 1. The journey takes about 4.4 years Earth time, but only about 70 days ship time. You'd experience only 70 days of travel, aging only 70 days, while Earth aged over 4 years. You could travel to Alpha Centauri and back in less than 5 months ship time, while Earth experienced almost 9 years. This sounds like a solution to the problem of interstellar travel. Just go fast enough, and time dilation makes the journey manageable for the crew. But there are 2 enormous problems. First, the energy required to reach these speeds is astronomical. Literally, astronomical. To accelerate 1 kilogram of mass to 99% of light speed requires about 600 trillion joules of energy. That's the energy equivalent of about 14,000 tons of TNT. To accelerate a 1-ton spacecraft, you'd need 600 quadrillion joules, equivalent to 14 million tons of TNT. To accelerate a 1,000-ton spacecraft, you'd need 14 billion tons of TNT equivalent. For comparison, the largest nuclear weapon ever detonated, the Tsar bomber, released energy equivalent to 50 million tons of TNT. So accelerating a 1,000-ton spacecraft to 99% of light speed would require energy equivalent to 280 tar bombas, and that's just to get up to speed. You'd need the same amount of energy again to slow down when you arrive. So you'd need about 560 Tsar bombas worth of energy total for a round trip. Where does this energy come from? How do you store it? How do you convert it to thrust efficiently? These are not minor engineering challenges. These are fundamental barriers that might be insurmountable with known physics. The second problem is that while time dilation helps the crew, it doesn't help the people back home. If you travel to Alpha Centauri at 99% of light speed, you experience the journey as taking about 7 months, but Earth experiences it as taking nearly 5 years. When you return, you've aged 14 months, but Earth has aged almost 9 years. Everyone you knew is 9 years older. Your children have grown up. Your friends have moved on with their lives. The world has changed. You've effectively traveled into Earth's future. This is time travel in a sense, but only forward, never backward. You can skip ahead in time by traveling fast, but you can never go back. And everyone you left behind has lived through those years normally, aging, changing, perhaps dying. This is the reality of relativistic space travel. It helps the crew by making journeys shorter from their perspective, but it doesn't help with the isolation, the separation from Earth, the fact that you're jumping forward in time and can never return to the time you left. There's also the problem of what happens if you hit something at these speeds. At 99% of light speed, a collision with even a tiny particle would be devastating. A grain of sand massing 1 milligram, hitting your ship at 99% of light speed, would release energy equivalent to about 42 tons of TNT. That's nearly as powerful as the atomic bomb dropped on Hiroshima. One grain of sand. Space isn't empty. There are atoms of hydrogen gas, dust particles, tiny rocks, all floating around. The density is low, but at relativistic speeds, even the thin gas between stars becomes a problem. You'd be plowing through this material at near light speed, and every atom would hit like a bullet. You'd need massive shielding just to survive the interstellar medium. And if you hit something larger, even a pebble a few millimeters across, your ship would be vaporized instantly. The energy release would be equivalent to thousands or millions of tons of TNT. Your ship would be destroyed so quickly you wouldn't even know what happened. There'd be no time to react, no time to steer around it. At 99% of light speed, you're covering about 186,000 miles per second. If you saw an obstacle 1 second ahead, it's 300,000 miles away, but your sensors detected it 1 second ago, so the information about the obstacle is 1 second old. The obstacle might have moved. And even if you could react, could you steer a 1,000-ton spacecraft out of the way in 1 second at those speeds? The forces required would be enormous, probably fatal to the crew. Realistically, you'd need sophisticated sensors scanning far ahead, mapping out the space in front of you, calculating safe paths around debris. But even then, you're betting your life that there's nothing in your path that your sensors didn't detect. One rock, one chunk of ice, one piece of debris from a destroyed comet, and your mission ends in a flash of gamma rays. These are the realities of interstellar travel at relativistic speeds. It's not impossible in principle. The laws of physics don't forbid it. But the engineering challenges are so severe that it's not clear humans will ever overcome them. Maybe some advanced civilization has figured it out. Maybe there are ways around these problems that we haven't thought of yet. But with our current understanding of physics, interstellar travel at high fractions of light speed seems almost prohibitively difficult. And at lower speeds, the journey times are so long that it's hard to imagine any human civilization committing to them. Who would sign up for a 43-year one-way trip to Alpha Centauri? Who would fund a multi-generation starship that wouldn't arrive for centuries? Who would send their children into space, knowing they'd never see them again, that they'd never know if the mission succeeded? These aren't just technological questions. They're profoundly human questions about what we're willing to sacrifice, how much we value exploration, whether we can think beyond our own lifetimes to benefit distant descendants we'll never meet. The speed of light limits us. It constrains how fast we can go, how quickly we can communicate, how far we can reasonably travel in a human lifetime. These constraints are built into the structure of the universe. They're not arbitrary rules. They're logical necessities that follow from the requirement that causality must work consistently, and they shape what's possible for any technological civilization anywhere in the universe at any time. We're not uniquely limited. Any alien civilization faces the same constraints. They can't go faster than light any more than we can. They can't communicate instantly across light years any more than we can. They're subject to the same laws, the same limits, the same fundamental structure of space-time. This is both humbling and equalizing. We're not special in our limitations. Every intelligence in the universe faces the same barriers. And if we ever do make contact with another civilization, we'll bond over this shared challenge, this common struggle against the vast distances and the finite speed at which information can travel. This is the reality of living in a universe with a finite speed limit. Space is big, and light is fast, but not infinitely fast. Distances that seem manageable in science fiction become nearly insurmountable when you account for the actual speed of light. Faster-than-light travel is a common trope in science fiction. Ships have warp drives or hyperdrives that let them cross the galaxy in hours or days. These stories need faster-than-light travel, because otherwise, the narrative would be impossibly slow. But, as we've discussed, faster-than-light travel would violate causality. It would allow time travel into the past, which creates paradoxes. Science fiction writers have invented various workarounds. Maybe you don't travel faster than light through space, but you create a wormhole that connects two distant points in space, allowing you to travel between them without covering the distance in between. This doesn't technically violate the speed of light limit because you're not traveling through normal space. Or maybe you warp space itself, contracting the space in front of your ship and expanding the space behind it. So you're not moving faster than light through space, but space itself is moving around you. These ideas are mathematically consistent with general relativity in principle, but they require exotic forms of matter and energy that might not exist. Negative energy, negative mass, things that we've never observed and that might be impossible. So while the equations don't absolutely forbid these things, nature might, we don't know yet. Right now, faster than light, travel remains firmly in the realm of speculation and science fiction. Every experiment ever done confirms that the speed of light is a hard limit. Nothing we've ever accelerated has exceeded it. And the energy requirements grow so steep as you approach light speed that reaching it seems impossible, let alone exceeding it. The universe appears to be telling us, quite firmly, that you can't break the speed limit. But why did the universe choose this particular speed? Why is light 300 million meters per second and not some other speed? This is a deep question, and the answer is that the speed of light isn't really about light at all. It's about the structure of space-time. In the equations of special relativity, there's a constant that appears. It's usually written as c, and it represents the maximum speed at which cause and effect can propagate. Light travels at this speed because photons are massless, but the constant c would exist even if light didn't. It's built into the geometry of space-time itself. The numerical value of c, the fact that it's 300 million meters per second, is actually arbitrary in a certain sense. It depends on how we define meters and seconds. If we use different units, the number would be different. In fact, physicists often use units where c equals 1. In these units, time is measured in meters, or equivalently, distance is measured in seconds, and the distinction between space and time becomes more apparent. 1 second of time equals 300 million meters of space in these units. This makes the equations of relativity simpler, because you don't have to keep writing factors of c everywhere. The point is that the speed of light is a conversion factor between space and time. It tells you how much space corresponds to how much time. And this conversion factor is a fundamental property of the universe we live in. We could imagine a universe where the speed limit was different, where c had a different value, but in our universe, it's what it is. And that value determines how fast things can happen, how far apart events can be while still being causally connected, and ultimately, how large the observable universe is. Now, there's one more aspect of the speed of light that I want to discuss, and it has to do with the relationship between energy and mass. Einstein's most famous equation is E equals mc squared. Energy equals mass times the speed of light squared. This equation tells us that mass and energy are equivalent. They're two forms of the same thing. You can convert mass into energy, and you can convert energy into mass. The factor that relates them is c squared, the speed of light squared. This is an enormous number. The speed of light is 300 million meters per second, so c squared is 90 quadrillion meters squared per second squared. In more conventional units, c squared is about 90 quadrillion joules per kilogram, or 9 times 10 to the 16th power joules per kilogram. What this means is that a tiny amount of mass corresponds to an enormous amount of energy. 1 kilogram of mass, if completely converted to energy, would release 90 quadrillion joules. That's roughly the energy released by 21 megatons of TNT, comparable to the largest nuclear weapons ever built. 1 kilogram, about the mass of a liter of water. If you could convert it completely to energy, it would release as much energy as a 21 megaton hydrogen bomb. This is why nuclear reactions release so much energy. When uranium or plutonium undergoes fission, the nucleus splits into smaller pieces, and those smaller pieces, added together, have slightly less mass than the original nucleus. The missing mass has been converted to energy according to E equals mc squared. It's not very much mass, typically less than 1% of the original mass. But because c squared is so large, even a tiny amount of missing mass produces an enormous amount of energy. In a nuclear fission reaction, about 0.1% of the mass is converted to energy. 1 kilogram of uranium, if you could fission all of it, would release about 90 trillion joules. That's equivalent to about 20,000 tons of TNT, 20 kilotons, roughly the yield of the atomic bomb dropped on Hiroshima. From 1 kilogram of uranium, this is why nuclear weapons are so powerful. They're converting mass to energy, and the conversion rate given by c squared is enormous. Similarly, in nuclear fusion, the process that powers the sun, hydrogen nuclei combine to form helium. 4 hydrogen nuclei fuse into 1 helium nucleus. The helium nucleus weighs slightly less than the 4 hydrogen nuclei combined, about 0.7% less. That missing mass is converted into energy. In the sun's core, about 600 million tons of hydrogen are converted into helium every second, and about 4 million tons of mass are converted directly into energy every second. 4 million tons per second. That's the rate at which the sun is losing mass, converting it into the energy that makes the sun shine. This energy, the energy from 4 million tons of matter being converted every second, is what heats the sun's core to 15 million degrees Celsius. It's what causes the sun to radiate energy into space. It's what reaches Earth 8 minutes later and warms our planet, drives our weather, powers photosynthesis, sustains all life on Earth. All of it ultimately comes from mass being converted to energy in the sun's core at a rate determined by E equals mc squared. The sun has been doing this for 4.6 billion years, and it will continue for another 5 billion years or so. In total, the sun will convert about 0.04% of its total mass into energy over its lifetime. That doesn't sound like much, but the sun is massive, about 2 times 10 to the 30th power kilograms, so 0.04% is still about 10 to the 27 kilograms. 1 million trillion kilograms converted from mass to energy. That's how much mass the sun will turn into light and heat over its 10 billion year lifespan. And all of that conversion, all of that energy, is described by Einstein's equation, E equals mc squared. But the equation doesn't just describe nuclear reactions. It's more fundamental than that. It tells us that mass is a form of energy. Any object with mass has an energy associated with that mass, even when the object is at rest. This is called rest energy. An electron sitting still has a rest energy of about 8 times 10 to the minus 14 joules. That's the energy equivalent of its mass, about 9 times 10 to the minus 31 kilograms. A proton has a rest energy of about 1.5 times 10 to the minus 10 joules. That's the energy equivalent of its mass, about 1.67 times 10 to the minus 27 kilograms. These are tiny amounts of energy on human scales, but on the scale of particles, they're significant. The rest energy of a proton is about 938 million electron volts. That's a huge amount of energy for a single particle. And it means that mass is really just a very concentrated form of energy. When you accelerate an object, you're adding energy to it. That energy increases the object's kinetic energy, its energy of motion. But because energy and mass are equivalent, adding energy is like adding mass. The object's inertia increases. It becomes harder to accelerate, not because it's physically getting heavier in the sense of containing more particles, but because the energy you've added contributes to its resistance to further acceleration. At low speeds, this effect is negligible. The kinetic energy you add is tiny compared to the rest energy, so the increase in inertia is not noticeable. But as you approach light speed, the kinetic energy becomes comparable to the rest energy, and the effect becomes significant. At 90% of light speed, the kinetic energy of an object is about 1.3 times its rest energy. The total energy is about 2.3 times the rest energy. This means its inertia has increased by a factor of 2.3. It's 2.3 times harder to accelerate than when it was at rest. At 99% of light speed, the total energy is about 7 times the rest energy. The object's inertia has increased by a factor of 7. At 99.9%, the factor is about 22. At 99.99%, about 70. The pattern continues without limit as you approach light speed. The inertia, the resistance to acceleration, grows without bound. To accelerate the object further requires adding more and more energy, and that energy adds to the inertia, making it even harder to accelerate. You're fighting a losing battle. The closer you get to light speed, the harder it is to go faster. To actually reach light speed would require infinite energy. Your energy would become infinite, your inertia would become infinite, and your mass would effectively become infinite. You'd need infinite force to accelerate further. This is why nothing with mass can reach light speed. The math literally forbids it. The energy required diverges to infinity as you approach c, and you can't have infinite energy. The universe doesn't contain infinite energy, so you can't reach light speed. You can get arbitrarily close, approaching 99.9999999% or even higher, but you can never quite reach 100%. There's always a gap, always a tiny remaining difference between your speed and the speed of light, and that gap is enforced by the structure of space-time itself, by the equation E equals mc squared, by the fundamental relationship between mass and energy. This is the ultimate speed limit. Not just a number, but a barrier built into the very fabric of reality. Only massless particles can cross this barrier because they don't have rest mass. They don't have rest energy that would need to be overcome. For massless particles, all their energy is kinetic energy, and they must move at exactly light speed. Not less, not more, but exactly at the speed limit. This creates the fundamental divide I mentioned earlier. Massive particles must travel slower than light and can exist at rest. Massless particles must travel at exactly light speed and can never be at rest. There's no middle ground. The speed of light is the dividing line, the boundary between these two categories of existence, and this boundary, this limit, is determined by c squared, the factor that appears in E equals mc squared. The speed of light squared is the conversion factor between mass and energy. It's the exchange rate, the number that tells you how much energy corresponds to how much mass. And because this number is so large, because c squared is 90 quadrillion, a tiny amount of mass corresponds to an enormous amount of energy. This is why the speed limit is enforced so strongly. As you approach light speed, your kinetic energy grows rapidly, approaching infinity. That energy has to come from somewhere. You have to put in more and more energy to go faster and faster. And eventually, you run out of energy. The universe doesn't have infinite energy to give you, so you can't reach light speed. The speed limit isn't just a law or a rule. It's a consequence of the deepest structure of the universe, the relationship between mass and energy, the geometry of space-time, the requirement that causality must work consistently. All of these things are connected. They're all part of the same unified picture that Einstein gave us. Special relativity, E equals mc squared, the constancy of the speed of light, time dilation, length contraction, mass-energy equivalence, all of it fits together into one coherent framework. One beautiful, elegant structure that describes how the universe works at its most fundamental level. And at the heart of this structure is the speed of light. 300 million meters per second. The ultimate speed limit, the conversion factor between mass and energy, the maximum rate at which cause and effect can propagate, the dividing line between massive and massless particles, the organizing principle that makes spacetime comprehensible. Not just a number, but a fundamental constant that defines the very nature of reality itself. So what have we learned tonight? The speed of light isn't just a speed. It's a fundamental constant that governs the structure of space-time. It's the maximum speed at which cause and effect can propagate, and it exists to preserve causality. Richard Feynman showed us that if anything could travel faster than light, the universe would be plagued with paradoxes. Effects would precede causes, information would travel backward in time, and the logical structure of reality would collapse. Different observers would disagree about the fundamental question of what causes what. Physics would be impossible. Science would be impossible. The universe would be a chaotic mess where logic itself breaks down. The only way to avoid this is if there's a universal speed limit, a maximum speed that's the same for all observers. That speed is what we call the speed of light, but it's really the speed of causality, the speed of information, the speed at which the universe can respond to events. Light happens to travel at this speed because photons are massless. But the speed itself is more fundamental than light. It would exist even if photons didn't exist. It's woven into the fabric of space-time, determining how space and time relate to each other, how mass and energy are equivalent, and how large the observable universe can be. The finite speed of light means that when we look out into space, we're looking back in time. The farther we look, the farther into the past we see. The light from distant galaxies left those galaxies millions or billions of years ago. We're not seeing them as they are now. We're seeing them as they were when that light began its journey. The observable universe is limited by how far light has traveled since the Big Bang, about 13.8 billion years. That corresponds to a distance of about 46 billion light-years in all directions due to the expansion of space. Beyond that distance, we can't see, because light from there hasn't had time to reach us yet. The universe might be much larger, possibly infinite, but our observable portion is finite, limited by the speed of light and the age of the universe. Every direction we look, we're looking at a different time period. Nearby stars show us the recent past, a few years ago. Distant galaxies show us the ancient past, billions of years ago. The cosmic microwave background, the afterglow of the Big Bang, shows us the universe as it was just 380,000 years after the Big Bang, 13.8 billion years ago. We're observers at the center of our own past light cone, receiving information from increasingly distant and ancient events. This speed limit also means that interstellar travel and communication are incredibly difficult. Even at relativistic speeds, traveling to other star systems would take decades or centuries from Earth's perspective. Messages would take years to cross the distances between stars. We live in a universe where space is big, and light, though fast, is not infinitely fast. The distances between stars are measured in light years, and those distances impose real constraints on what's possible. You can't just hop in a spaceship and visit another star system for the weekend. The journey would take decades at best, centuries at worst, with enormous technological and human challenges at every step. But the speed limit also gives the universe structure. It creates the light cone structure where every event has a past that could have influenced it and a future that it can influence. It ensures that causality works, that causes precede effects, that the universe makes logical sense. Without the speed limit, reality would be chaos. With it, the universe is comprehensible, governed by laws that we can understand and test. Einstein's theories of relativity, both special and general, are built on the foundation of the universal speed limit. These theories have been tested countless times, in laboratories, with satellites, with particle accelerators, with astronomical observations, with gravitational wave detectors. Every test confirms that relativity is correct. Time dilation is real, measured with atomic clocks. Length contraction is real, observed with particles in accelerators. Mass-energy equivalence is real, demonstrated in nuclear reactions every day. The speed of light is truly the ultimate speed limit, not because nature is being arbitrary, but because logic demands it. Feynman's insight was that this isn't just a law of physics that we discovered by experiment. It's a requirement of reason itself. If the universe is going to make sense, if cause and effect are going to work, if we're going to be able to have a coherent understanding of reality, then there must be a speed limit. And once you accept that there must be a speed limit, once you demand that the speed of light must be constant for all observers, all the strange phenomena of relativity follow inevitably. Time dilation, length contraction, mass-energy equivalence, the relativity of simultaneity, all of it flows from the single requirement that the speed of light must be the same for everyone. This is the beauty and power of physics. Deep truths about the universe aren't arbitrary rules handed down by nature for no reason. They're logical necessities, things that must be true for the universe to be consistent. The speed of light is such a truth. It's not just a number we measured with instruments and wrote down in textbooks. It's a fundamental constant that defines the structure of space-time itself, that makes causality possible, that allows the universe to be a place where science can be done and knowledge can be accumulated. And understanding why it exists, why it must exist, gives us a profound insight into the nature of reality. We've seen tonight that the speed limit isn't a constraint placed on us by a capricious universe. It's a gift that makes the universe comprehensible. It's what allows logic to work, what allows causes to precede effects, what allows the past to be fixed and the future to be open. Without it, time would have no arrow, causality would have no direction, and reality would make no sense. With it, we have a universe where knowledge is possible, where science works, where we can build up understanding piece by piece and be confident that our discoveries are real and reliable. The speed of light is the foundation of that confidence. It's what makes physics possible. It's what makes the universe make sense. Tonight, you've learned that the universe has a speed limit, not because of some arbitrary cosmic regulation, but because logic and causality demand it. You've learned that this speed limit is the same for all observers, leading to the strange and beautiful phenomena of special relativity. You've learned that mass and energy are equivalent, related by the square of the speed of light, and that this equivalence explains everything from nuclear reactions to why you can't accelerate to light speed. You've learned that when you look at distant stars and galaxies, you're looking back in time, seeing the universe as it was, not as it is. You've learned that the light cone structure of space-time determines which events can influence which other events, creating a causal structure that all observers agree on, even when they disagree about timing. And you've learned that Richard Feynman, with a simple thought experiment about what would happen if the speed limit could be broken, revealed why it can't be. Faster-than-light travel would allow time travel to the past. Time travel to the past creates paradoxes. Paradoxes destroy causality. Without causality, the universe makes no sense. Therefore, the speed limit must exist. And that speed limit, whatever it is, must be the same for all observers regardless of how fast they're moving. In our universe, that speed is approximately 300 million meters per second. We call it the speed of light because light travels at that speed, but it's really the speed of causality, the speed of information, the speed at which reality itself operates. So, the next time you turn on a light, or look up at the stars, or think about the vastness of space, remember that there's a speed limit out there, a speed that nothing can exceed, a speed that preserves cause and effect, that connects space and time, that makes the universe comprehensible. The speed of light isn't just fast, it's the speed at which reality itself operates. And that's far stranger and more beautiful than just being a number we measure. It's a fundamental truth about the nature of existence, a logical necessity built into the very fabric of space-time. It's what makes the universe a place where knowledge is possible, where science works, where causes precede effects, and the future is genuinely open. The speed of light is the ultimate speed limit, and it's the key to understanding why the universe is the way it is. That's everything for tonight. If this journey through the fundamental structure of space-time changed how you see the universe, I'd love to hear about it. The universe is full of deep mysteries, profound truths hiding beneath the surface of everyday experience. We've explored one of those truths tonight, the nature of the speed limit and why it must exist. But there are so many more waiting to be discovered, so many more questions to ask, so many more insights to uncover. The universe is strange and beautiful and comprehensible all at once. We can understand it, we can make sense of it, and we can marvel at how elegantly it all fits together. The speed of light is just one piece of that puzzle, but it's a crucial piece, the foundation on which so much of modern physics is built. Thanks for joining me on this exploration of why nothing can go faster than light and what that tells us about the nature of reality itself. Keep looking up, keep asking questions, and remember that the universe, for all its strangeness, is ultimately knowable. We can figure it out, one insight at a time, building understanding piece by piece. And sometimes, the deepest insights come not from complicated mathematics or elaborate experiments, but from simple questions asked by brilliant minds. Questions like, what if we could go faster than light? Feynman asked that question, followed the logic to its conclusion, and revealed why the answer must be no. The universe has a speed limit, and that speed limit is the key to everything. It's what makes reality real.